Good afternoon, ladies and gentlemen. My name is Dale Credland from WindowMaster. I've been with WindowMaster for nearly 5 years now, business development manager for the UK and Ireland. So today we're going to talk about some intelligent natural ventilation and how we can hopefully avoid some common pitfalls and some of the design challenges that are often faced. So first and foremost, I'm going to talk about who WindowMaster are, some of the perceived challenges of natural ventilation, benefits of nat venting and nighttime cooling, principles of natural ventilation, the advantages of automated nat vent, the importance of fine control, achieving effective natural ventilation solutions. Then we're going to cover some important considerations. We have some project examples right at the end of the seminar as well, which we can go through in a bit more detail, and then we can have a bit of a Q&A at the end. So first and foremost, a little bit about WindowMaster's history. Well, way back in the 1940s, when Willem decided to invent his first roof light, it was determined very quickly that using a large stick wasn't going to be the most effective way to open up these windows. So he basically got something akin to a bike chain and put a motor in a wooden box. And that was really the first development of window actuators, all the way back in sort of the mid-1940s. And then from there, things sort of developed into what you see in front of you today, which is WindowMaster today. So we were the electrical division to Velux until sort of 1990. And then beyond that, we gained our own identity as WindowMaster. Up until 2015, we were still part of the Velux group. And in 2015, we got bought by a private Danish business investor. So our heritage is still very much Danish. So our HQ is in Denmark, in Vedbæk. All of our production capability is over in Germany. We have 7 different sales offices in 7 countries, the UK office being down in Kettering. And we've got over 1 million actuators out there in the marketplace currently. So serving 20 countries. And we also work with certified partners, and we have 30 of those across the globe. And we've got experience in much over 1,000 major projects. So lots of experience in the market of natural ventilation. So why are we here? Well, we design and manufacture actuators and controls and intelligent natural ventilation smoke solutions. Basically, over the last 20 years, we've been working with people like Mott MacDonald, Max Fordham's, WSP, Arup, Bureau Happold, BDP, just to name a few. Trying to stay ahead of the curve of the natural ventilation principles, the regulatory, the reforms, all of that information that we need to comply with. And we work with local architects, consultants, builders, subcontractors, hopefully to give you some sustainable building advice and most definitely energy efficient buildings. So the solution overview, as you can see, over on the left, first and foremost, actuators, which we offer for roof lights, windows, and then motor controllers. There is a key tie-in with motor controllers and actuators, which I'll talk in a bit more detail about as we go through the presentation. We also offer smoke ventilation panels, and again, this is critical when we're looking at EN compliant solutions. And also the intelligent controls. So when we're looking to maybe have something a little bit more sophisticated than what the BMS systems can offer currently. So what is natural ventilation? Well, quite simply, we're trying to carefully harness nature's forces to move just enough air through the buildings in the right way and at the right times to create great spaces that are comfortable, productive, and energy efficient, eliminating or significantly reducing the need for mechanical ventilation. I'm very lucky that we work in the Kettering office in such an environment, which is really such a showcase of the fantastic products that we have. So there are many challenges indeed in getting a suitable natural ventilation system working, and we come and speak to people on a regular basis about these challenges, and we hear lots of horror stories. But a lot of the common pitfalls, unpredictable performance sort of strikes highly at the top, overheating and poor air quality. So that's more where manual windows are in play. You've got to actually physically have somebody to open that and close that window. So that can be a challenge in itself. Good design, but poorly specified. So we've spent time getting to grips with the design of things, putting the design into place, and then it gets VE'd, which is very frustrating for everybody concerned. Poor control and complaints of cold drafts and high energy usage. Again, we've got lots of clients that have suffered with this over the years. But also acoustic issues, and this can come from external sound transfer, but more often than not, it's actually the actuators themselves that can emit significant amounts of noise and put off people that are trying to work or study in the environments that actuators are in the systems of buildings of. So health and safety can be a concern. So things like trapped fingers and security, compromising risk of insurance is always something that needs to be considered. And obviously then the perceived performance of mechanical systems. And again, but what cost does that have to the building owner? So why use natural ventilation? Well, put simply, properly designed, specified and delivered natural ventilation can deliver great performance. Better spaces, lower costs with significant energy savings compared with mechanical alternatives. And we're going to dive in and explore some of those systems and some of the comparisons between the costs of those. So if we look first and foremost at the slide here with primary energy consumption, we can see natural ventilation versus mechanical ventilation versus mixed mode ventilation. And we can see there the fan electricity versus the heating being the primary energy consumption, in Copenhagen, Munich and London. You'll note that there is a small increase in the amount of heating energy used with natural ventilation solutions. This relates to providing a good air quality in winter and a small amount of associated heat loss. When properly controlled, this is minimal, and overall, there are still significant savings. So if we look at the installation costs of naturally controlled versus Aircon Basic and Aircon Advanced, in terms of the capital costs, independent studies demonstrate equipment saving using automated natural ventilation compared with basic centralized and advanced mechanical systems is approximately 7% increase in costs, and Aircon Advanced will result in a 20% increase. This information has come from Gardner Theobald and is an independent research agency who were commissioned by CIBSE to research the benefits of natural ventilation over air conditioning. Again, if we look at the the lifetime cost and life cycle costs, again, across the three systems, we can see some dramatic differences, certainly with the mechanical ventilation. But don't just take our word for it. We've done quite a lot of work and understanding what the Carbon Trust have found, and studies show from the Carbon Trust that naturally ventilated buildings save between 24 and 71% of carbon emissions, and on average £30,000 a year in energy per building, which is a pretty good saving, I have to say. They clearly state that the designers should make the decision early on whether to naturally ventilate the building before it's designed and consider mixed mode ventilation, when full nat vent is not possible. It's also in natural ventilation is also a key part of the London plan, encouraging building designers to adopt energy efficient measures as part of the cooling hierarchy. Can't read my own notes, apologies. Approach to the design, encouraging the use of thermal mass and passive venting wherever possible. So this slide's quite interesting. If we look at the health issues relating to ventilation, as well as the cost saving, there are also significant health benefits and well-being to consider. Buildings using natural ventilation have been proven to be more productive with less sick days. If you've heard the term sick building syndrome, it's constant return, better feedback on occupants, satisfaction. There may be a little artistic license in these pictures, obviously looking at the beautifully crafted Danish window actuators versus the internal workings of a mechanical system that hasn't been cleaned, but still it gives you a good indication. And again, the source information has come from Mayer 2008. And again, if we look at the health symptoms, dizziness, concentration problems, fatigues, headaches, throat irritations, and so on, you can see that all of these symptoms are dramatically reduced when utilizing natural ventilation over a mechanical solution. So some more on benefits then. We have space-saving solutions. So again, this is Hayward's rule of thumb from BISRA 1995. And basically, with natural ventilation, you don't need the plant rooms, the ductwork, new filters, duct cleaning. Some significant benefits to having natural ventilation. So continuing on that trend, advantages of natural ventilation and mixed mode. You can see for yourself the energy savings, the healthier environments, performance related to classroom studies, in terms of 7 to 8% increase in children's learning, 18% in productivity gains over a mixed mode and air-conditioned solution, and then a reduction in costs as well. Some significant cost savings to be had, certainly over the life cycle and the lifetime of a building. So in terms of principles of natural ventilation, these are the fundamental principles. So predominantly, the first thing that we need is wind pressure. Now, luckily in the UK, we have wind pressure approximately 90% of the time. And then for the other 10% or so, we can use the likes of thermal buoyancy, the temperature differences that you can see there. Again, we've also looked at some different designs in terms of the shape of the building. And in some cases, we've certainly seen some designers sort of push the envelope in terms of double skin facades, helping to promote the control of air movement. It's always really early in the project design that it's considered whether natural ventilation is going to be suitable or not. So in terms of the basic ventilation principles, we can see the first slide on the left, the single-sided ventilation. So this is literally where we've got venting from one side. And there is a rule of thumb which comes from the AM10 document, which typically limits the design of your floor plate in terms of the depth of the room by 2.5 times your floor to ceiling height when designing for natural ventilation with single-sided buildings, single-sided rooms. Where we've got cross venting, that figure doubles to 5 times the floor to ceiling height. And again, cross ventilation is where we've got vents on either side of the room itself. And then stack venting, which is low intake and high extract through, for example, roof lights or sort of atrium style layout. So in terms of nighttime cooling, this is such an important factor when it comes to natural ventilation strategies. By using the cooler air at night and automated openings, it can be possible to cool down indoor spaces and reduce the temperature of the fabric and contents of the building. To prepare that fabric to be able to absorb some of the latent heat the next day and keep air temperatures much lower and much more comfortable. Thermal mass helps to significantly increase the benefit of nighttime cooling and stable air temperatures. But even in a typical medium mass building, nighttime cooling has a significant impact. Looking at the analysis above, on the left side, we can see that the typical middleweight build with the yellow bar is exclusive of holidays. So it's a school basically, and the summer holiday. And we can see that the nighttime cooling reduces the number of hours above that critical 26 degrees by over 60%, which is phenomenal. It also has the potential to reduce peak temperatures by up to 10 degrees, which again is fantastic in itself. And that is where you're going to see such an awful lot of energy reduction, because you're not having those fans as part of the air conditioning solution on running to reduce the next day's temperature. If we can do that naturally by utilizing high level opening windows, then that is the way to do it. So what we tend to do is we'll look to maximize the space. We'll look at first and foremost a whole building strategy to gauge exactly what we need. But if we look at an individual room requirements just on the right, we can see that first and foremost, we unfortunately do need a weather station up on the highest point of the roof. And this is obviously to determine wind speed, in some cases, wind direction, and also if it's raining or not as well. And then coming down into the building, we can see that we've got temperature, combined CO2 and humidity sensor. We've got some high level openings to the right there. And then we've also got a manual override keypad. Again, just to give the users a little bit of control themselves in the room. We've found that in many cases, if there hasn't been any manual override switches incorporated into a solution, into a system that we've put into a building, often it's noted by the occupants. People want a little bit of user control, and that's very important over studies that we've seen over the years. So in terms of a stable indoor climate, it's important for us to understand that natural ventilation has to react to a number of variables. It needs to be intelligently controlled for start. It needs to be a stable environment and good levels of performance. And the demand for ventilation in spaces changes during the day. And as you can see, some of the factors above in terms of occupancy, heat loads, solar gains, outdoor temperatures, wind speed, and wind direction is constantly and can constantly change. Obviously, the CO2 levels can rise, which hopefully won't be a sign of my presentation. If you're feeling drowsy, that would be the score. But you can see there as well the things that we factor in: the user comfort, the air changes, some of the draft and cold problems, the insufficient air change, and of course the optimum window position, which is really quite key. So a number of years ago, we decided to do some wind tunnel testing, just to sort of illustrate really three different types and styles of opening window. And the reason why we carried out this study was to assess wind flow through the vent at different opening positions and obviously the different window openings. This was in a cross-venting scenario. And if first and foremost we concentrate on the green curve, this is a top hung outward opening window, and this is what you would see on most buildings. We would expect that when we see the window is closed, the airflow, we would hope, is zero. However, we might expect that as a window is opened, the increase in airflow is linear. In fact, we found that due to the air pressure differences each side of the vent at relatively small openings, you can observe relatively high airflows. For example, at 10 millimeters of opening, you can see almost 65% of the airflow of a fully opened window. You'll be familiar at home as well if you've ever opened your patio doors on a day like today, if it's nice where you are. The quite large amounts of wind that you can get through such a small gap. Again, if we look at the 50 millimeter opening for that, 96% of the overall ventilation requirement was achieved at 50 millimeters with a top hung outward opening window. We can see there at the far end, the bottom hung inward opening window is the worst performing. So at 50 millimeters, we're achieving about 70% of the overall ventilation requirement. And somewhere in the middle is a parallel opening window. And again, at 50 millimeters, we can see that we're achieving about 91% of the airflow. So this really starts to point in the direction of really thinking about how much we've got those windows open, how much control do we actually need over these windows? And it starts to show that actually we need quite a great amount of control over them to hopefully get away from buildings that suffer from poor energy performance and complaints of drafts. So introducing natural ventilation option 1, which is manual control. I think you'll agree that this is generally at the top of most people's lists in terms of the overall cost initially, but generally when things are being value engineered, this tends to happen quite frequently. But what about the energy performance, and how good is the space to be in? Well, the first challenge is the CO2 levels, and unfortunately they can rise up to 4,000 parts per million very, very quickly. Within 25 to 35 minutes, those CO2 levels can reach 4,000 parts per million. The challenge is then how long it takes to then dissipate back down to an acceptable level, which in the cases of BB101 would be 1,500 parts per million. Well, that takes about, again, between 25 and 45 minutes to then dissipate back down to an acceptable level. So that is a long time that the CO2 levels are far beyond what they should be, certainly for a learning environment. The other challenge is, again, we've used this as an educational room, so it's a classroom. So we have our systems and we can monitor our systems to be able to see exactly how they're performing in terms of not just the opening distances, but again in terms of the CO2 levels, the temperature, which we can monitor. On an average, if we looked at a single typical classroom with 4 windows, each classroom window would move about 40 different times a day, which would roughly be 160 times that window would move. Now, the challenge with that is obviously if you're trying to teach a class and also manage 32 children and possibly a teaching assistant, that is an awful lot of movement that you're going to have to make. Also, it's actually getting to those windows. So again, it depends on the layout of the classroom. For example, if there's tables in front of the windows, how effectively are you going to be able to get to those windows? So that's a big challenge. Also, if we've got high energy usage, because the windows are being left open because they're manual, so people can forget about them. People can obviously leave them open far too much. And as we've looked at and explored in the previous slide, we don't need the windows to be thrown open, for example. But some of the other challenges as well, so security, that would have a significant effect if we were trying to look at doing and utilizing some nighttime cooling. I would suggest maybe not leaving windows open in this scenario. And again, in the occupants are more likely in the winter to actually close the windows rather than turn the heating up. So again, there's a challenge there between systems, between whatever the heating's doing and getting your ventilation requirements. So the potential consequences of manual control, well, the windows are either left open far too much or closed for far too long, poor air quality and overheating, disruption to occupants, and high energy usage. So if we look at the comparison that we did a few years ago now at Untermust in Zurich, what we wanted to do was look at the comparison of manual systems versus automated control. Now, this was also looked at for energy consumption as well as CO2. So hopefully we've sort of covered all the bases. So you can see the section of the 2 floors that we looked at, and you can also see the floor plans as well. So this study was done between basically the end of June and the 10th of July. So again, we've got high outdoor temperatures. So that was kind of key to do it in a warm period of the year to obviously help show and reflect, hopefully, some positive effects of different systems. So this was done across 3 rooms, so 3 different zones. So what we had was 3 zones with manual windows and 3 with our automated system. And on this one, you can see the automatic window comes out much more effective in terms of managing those temperatures. In what I have to say, if you look at the outside temperature is sort of just below 30, and then it tips above sort of at the beginning of July. There you can see we're dealing with some hot temperatures. So, and again, the hand operated, if you look at the hand operated window, 22 to 25 degrees there, that is, it never even achieved, it never even got down to that temperature. It just started at warm. So the inside temperature there, you can see, has had a massive difference. Only just over 20% of the time it was above 26.5 degrees with automatic. So if we look at the comparison of the air quality, so the CO2 concentration, and the heating energy consumption, we can see again across the different zones. So we can see the automatic and the hand on the left, the hand operated windows there. And this is a really good reflection of the CO2 concentration being managed effectively by the WindowMaster solution versus the hand operated. And then again, if we look at this, the second classroom with automatic and hand operated, again we can see that the CO2 levels, they're actually in the comparison is the left slide is in the summer and the one next to it is in the winter. So we can see that again with hand operated windows, because they haven't been opened, you can see that the CO2 level isn't managed at all. Whereas obviously with the automatic in the winter, we can see a big difference between the CO2 levels. And again, if we look at the heating energy consumption, we factored that a 15% energy saving with automatic window, or with automation, sorry, compared to manual windows is a very healthy cost saving in terms of energy consumption. So we try and take a much better approach at WindowMaster in terms of trying to look at things holistically, trying to join up the principles between energy consultant or consultant and architect, and hopefully carrying it right through to hopefully join up the loop. Nobody wants to see any of these design faux pas. I think it's fair to say. So let's dive in and have a look at how we can achieve some effective natural ventilation. This is with intelligent control, so this is where we start to get to the good stuff. So what does it look like? Well, in our experience, these are key factors to make sure that the strategy works. Distributed openings, carefully controlled in response to air temperature and quality, balanced with outdoor weather conditions, a really smart nighttime cooling strategy to prevent under or overcooling and obviously to protect the assets of said building. Single source supply. This takes out so much of the challenges that we see on such a regular basis. And if you look at the complete solution design, so design, components and controls, and the control solution, if we can start to keep all those under one roof, we can really start to minimize the effects of poorly designed natural ventilation. So basically, good controls using actuators, the linking of the control systems, whether that be standalone or whether it be integrated with a BMS, and then that complete solution. That's how we help our clients eradicate a lot of the challenges that they face with natural ventilation. It's also good to understand what the optimum window arrangement looks like. So normally, if we can look at automating high-level windows and having low-level manual windows, this gives a sense of the user control, but also it does its clever stuff at the high level in the background. Obviously, if we've got mid-level open windows and we've got it's a nice blustery day and we're trying to work, we don't want papers blowing all over. Similarly, as well, in the winter, we don't want the occupied zone to be feeling cold and the occupants to be feeling cold. If we can open up the high level windows using automation and fine control, we can minimize the effect of cold air dumping. And actually, we've actually proved with internal CFD analysis that we can overcome those objections and challenges of cold air dumping. So in terms of product solutions and design support, there's many different ways that we can look at utilizing actuators on Windows. I think the key thing really is to call as early as you can in the design process. We can help you select most certainly the best actuator, the most suitable in terms of chain lengths, in terms of opening areas that we need to achieve, but also in terms of the number of actuators per vent. That can be critical when we're talking about much larger openings and obviously the forces that are required to open such windows. But also we can look and hopefully help with some of the aesthetics and practicalities in terms of the wiring routes and maybe how we can look at blending in the actuator with the window or hiding it completely, as we often get involved with now. So controlling natural ventilation option 2. This is all to do with BMS control. So on the outset, BMS systems have good capacity depending on how good they've been programmed. So some of the challenges really around this is the capabilities of the BMS guys to eliminate lots of variables. So generally they're looking at the temperature of the building, whether the lights are coming on in a room or not. And this can often lead to not as sophisticated algorithms for your BMS system to control natural ventilation. So the first thing that we look at is, in terms of the control, is the use of 0 to 10 volt timed controlled solutions, which is often where some of our customers come unstuck. So it's basically the BMS will send a signal to the actuator, but there can be a number of things happen between the actuator and the power itself. They can have voltage drop. And unfortunately, one of our clients suffered this last year over in the northwest of England, where they've got a university which was brand new in design. It was literally opened the same year, and they had some roof lights which were stuck open for the majority of the winter because of volt drop. The BMS basically lost the actual position of the roof light actuators, so it didn't know that they were open when they were. Now, as you can imagine, the energy manager for said university was not very happy to learn that the roof lights were open all through the winter, when he's obviously trying to achieve his 2020 targets in terms of energy reduction. Moving on, if we look at the basic incremental control, often BMS companies will give you some incremental control of the actuators, and this means that they'll say, we'll maybe give you 4 different opening positions of the actuator within the window. However, if you've got an actuator that opens 500 millimeters, this would mean that you have got an incremental opening distance of 100 millimeter. And sometimes, in some cases, the BMS companies don't even put an incremental opening distance on, so they will just, the BMS, the CO2 sensor and the temperature sensor will read that there's a requirement for fresh air, and it will just literally throw open the windows as wide as it can, which is not very effective, as we've learned on previous slides, certainly with the wind tunnel test slide. This also leads to one of the biggest complaints that we see as WindowMaster, is that people often talk about the noise that's emitted from other people's actuators. Because there's no variable speed, they just literally open and close, and that can lead to significant noise from these actuators. So much so that we've taken some videos in the past which we show in CPDs when we go out to see architects and consultants, and often you can see people grimacing in the room as they watch it, thinking, oh my, why did I not put a motor-link specification on the building that I've just designed? There are also potential health and safety issues. With no feedback to the actuator, how would you possibly know if there was anything trapped in between the leading edge of the window and the window that's closing itself? So that can be a big problem. Possible use of 240 volt actuators. So again, you would need to have more containment, and possibly there'd be overheating issues. Again, mentioned, there's limited ability to program many actuators that are out there on the market. So in terms of basic programming for nighttime cooling, wind, rain-ect, that can also be a challenge, because if you've got windows that have got 4 or 5 incremental openings and the sophistication of programming isn't there, then if we've got a nighttime cooling strategy, we don't want the windows left open at 500 millimeters. And this is, again, something that I've come across many times with my career with WindowMaster. The use of third-party components means that the responsibility of the package gets diluted somewhat. And our package often gets split between the window manufacturer or the facade consultant, the M&E contractor, the BMS, sometimes a main contractor, sometimes the electrical package. But again, if you've got different components being bought from different places, they haven't been tested together, it's not proven that it will all work. And often when it comes to the projects being handed over, then that's when we get a call to say, can you help us, because nothing seems to be working. So this leads really to limited knowledge of natural ventilation principles, can often be and result in really quite negative experiences of natural ventilation projects. Thankfully, there is another way, and this is something that I'm really passionate about in terms of the technology. And this really, MotorLink, is what sets WindowMaster apart in this industry, and really kind of means that we're number one when it comes to performance. MotorLink is really, the consideration that needs to be taken into account is that the actuator and the motor controller must be paired together. So if we don't have our motor controller controlling the actuators, we don't get any of the good stuff that we see at the bottom from a networked perspective. So if we look at accurate positional feedback and control on the motor line, that comes as standard with MotorLink. So we get feedback on the ventilation on the vent itself to within 1 millimeter, 1% accuracy. And again, when we're talking to estates directors and estates managers of large university buildings, they look relieved when we talk to them about this in particular. This is a massive problem for these estates guys. One of the other challenges I started to talk about previously was the noise that some of the actuators on the market emit. Again, if you've ever had the pleasure of hearing one of our actuators, you will note that it is whisper silent. It's almost silent. We have got acoustic tests on the majority of our actuators, and very recently won a very large project over in Manchester as part of the performance as well as the acoustic performance. The client actually stipulated that they wanted actuators that were near silent. And again, we have got some specification text for MotorLink and some of the other systems that we do, which again, if required, I can send you after the presentation. Again, these are performance based rather than anything else. So it hopefully will ensure that we can drive this controllability through the specification process and have it delivered into the projects. You'll note that on there as well, we have a pressure safety function. So again, if the windows are at high level, that's already a good start in terms of obviously managing the cold air and the draft issues that we could have, but also it always minimizes the chances of anybody getting anything stuck in between the window and the leading edge of the window frame. So we have a pressure safety function. So the actuator, if there is anything stuck between the window and the window frame, will realize that it's drawing more power from the motor controller and actually back itself up and open so that we don't get anything stuck in between the window. But you will note that we still need the intelligence and the proven algorithms to drive this fantastic piece of equipment that we have called MotorLink. So this schematic really just shows the MotorLink BMS integrated controllers. So some key benefits and points to realize. First and foremost, our motor controllers can operate the actuators from up to 50 meters away from the actuator itself, which means that when we're designing, when we're in design phase, we can easily design our panels to be hidden out of the way. So for example, under roof tiles even, as long as it's not for an EN smoke solution which would require battery backup, we can mount the panels in such a way to the soffit underneath. But also you'll note that we can group motors together in different zones. And again, this is a massive benefit to what else is out there in the marketplace in terms of actuators and controllers. Many of our competitors don't have the ability to do this, so they would actually need a motor controller per zone. We can supply 20 actuators with just one panel. So there's some significant cost savings there, because obviously we would need a 13 amp fuse spare to power each motor controller. And again, there on the network, you can see the different zones, the temperature and the CO2, and the weather station, of course. So controlling natural ventilation, option 3. This is really where our years of speciality and specialism can help you in your projects going forward. So in terms of concept and design review support, looking at the overall control strategy, we've got certain other offerings that are chargeable, steady state calculations, full dynamic analysis, etc. But more importantly, what we'll try and do is tie in close the loop between the builder, the M&E contractor, the window fabricator, and the BMS company when it gets to delivering the project itself. And then in terms of design of the control, simple, proven, smart control algorithms, which is really key to getting that fine control. The installation, the commissioning, and the training, and the service and the maintenance. So we really do take a holistic view from that standpoint. We don't just want to sell products. We want to ensure that we're getting the whole process done effectively in the right way. So again, you'll see the control system example here, and again on the bus network, you can see various actuators and panels. As I mentioned before, we can have 20 actuators off one panel, one 20 amp panel. We do 20 amp panels and 10 amp panels, but again, we'll help you select that based on the design and layout of the project. Again, to minimize the cost, but also to maximize the effectiveness of the solution. So MV Comfort is perfect for smaller zones. We tend to get involved a lot with school extensions where we've maybe got sort of 4 or 5 classrooms, maybe a dining hall, and maybe a sports hall as well. And this is great where we've maybe got no BMS system at all. It's maybe an older school, or There is maybe a BMS system in there that would like to read what our solution's doing, but this is from basically, well, from 2 zones right up to 8 zones. And again, if we look at the comfort system and we can see the functionality, I'll talk about that in a bit more detail, but we can see the schematic there. We can also control other people's equipment. We can see the roof turrets up there as well, and obviously the fan assisted, so other people's fans. We get involved in controlling other people's equipment quite frequently. So MV Advance is where we may be looking for something a little bit more sophisticated on much larger buildings, and this is certainly a significant turnkey solution for those larger projects. So the benefit, or one of the main advantages of NV Advance, is the CFD analysis that we do. So what we would do is, once we've won the order, we would, to gain specific controls for this, for the individual project, we would look at the building from and the openings from 16 different angles to determine the CP values. So basically looking at how the wind performance, how the wind is hitting the building, and where the high points of wind pressure, and where the high points of suction are. So if you can see from the design there, we've got the blue is where there's probably a little bit more suction, and then where we've got high points of wind pressure are noted in red. So this is an example from Telford, and this is the Hadley Learning Centre. And again, this just basically shows the CFD model of wind pressures according to the wind direction, and how we looked at basically building in the control algorithms. So the average open distance then, so we talked a little bit about this before, but MV Advance helps deliver the optimum temperature and energy performance, and it's all through those high level openings. So what we did was, to give you an example of this, we dialed into one of our schools, which is Kingsmead School. This information basically shows the opening low facades, the opening high facades, and the skylights, and the time that's opened, the amount of opening space that is on those windows. And to the left there, you can see the window that's open. We've taken a picture in 5 mil increments. So to summarize, NV Advance, it's one turnkey package, proven control algorithms, optimization using CFD for best building, performance and comfort, coordinated delivery, intelligent day and night control and cooling strategies, whisper quiet automation, year-round control, BMS friendly via interfaces, obviously utilizing hybrid and taking into account things like solar shading, simple interface and monitoring, and optimized site visits as well. We offer 4 of those throughout. So very quickly, time really has run away from us, but it just gives me time, hopefully, to talk about MV Embedded, which is a flexible, tailored solution, which is new to the market for us, and it's really quite an exciting time for WindowMaster with launching this to the market. It's proven intelligence for natural ventilation and mixed mode solutions. We can actually control lots of other people's equipment with MV Embedded, other people's fans, roof lights, heating, and so on. It's totally BMS compliant. You can also manage it from your mobile, and it's also cloud-based as well. Now, because we have actually nearly run out of time, ladies and gentlemen, I was going to skip through and just show you a couple of some of the very last slides, because there's some great tools. Unfortunately, we haven't had time to look through the project references. However, our website really is fantastic. If you want to head over and have a look at some of the case references, certainly some of mine, I cover the north of the UK and Ireland, and I've certainly just put one on there for a housing association office that I completed a couple of years ago. That was up in Scotland, but there's some great references on there, ladies and gentlemen, so please feel free to go and have a look. And alternatively, as well, we have just launched this fantastic new tool to the market, which is our new actuator finder. And again, if you look at the just this slide example there, if you go to our website, you can basically select your window sizes, dimensions, glass thicknesses, what position your windows are in terms of the orientation, top hung, side hung, etc. And you can choose your ventilation spaces that you're looking to, obviously with the main throat of the window, or maybe including your side triangles as well. Put in that information, and then what you can do is you can get a suggestion on what actuator would be best suited to your project and your window. You can also save it to a PDF. You can get an offer as well, but I really highly recommend checking out the actuator tool finder. So, ladies and gentlemen, thank you very much for your time. I'm sorry we sort of didn't get to look at some of the projects. I'll happily take questions now if anybody has any, but alternatively, you can sign up to our newsletter. That's at windowmaster.com. And again, if you have any requirements or immediate sort of project requirements that you would like to talk about with us in more detail, you can email us at info.uk@windowmaster.com. And thank you everybody for joining me today. I hope you found the time valuable, and yeah, I'll happily look forward to working on any projects with you in the future as they're required. Thanks very much. Thank you. Goodbye.